So in lecture, we wrapped up the conversation about friction, forces in general, and the main goal then was to do a bunch of practice problems. We are limited in time in class, especially if they are springing unexpected fire drills upon us. So what I'm going to do now is work on 5 select problems that should cover the span of style that you're going to see, in most of the problems you'll work with on your practice exam. Now, let's start taking a look first at the coefficients of friction. As it's wrapped up, you can see the coefficients of static friction on the left side, the coefficients of kinetic friction on the right-hand side. You got the image shown here with the increasing value of static friction. Remember, you can push on a heavy object a little bit, push on a little bit more, and eventually push it, it begins to move. That's what you're seeing here. The maximum value for static friction is going to be higher than the average value of the kinetic friction, which is basically a constant for once that object is moving relative to the surface that it's in contact with. Here's a table on the right hand side of several different surfaces in contact with each other. Take a note of the relative details for the static coefficient of friction and kinetic coefficient. The kinetic coefficient is much lower on average than the static coefficient. Now, some variations like ice on ice is going to be a lower relationship, whereas rubber on concrete, you've got a high static coefficient and still relatively high for kinetic, and so forth. So just take a look at this. This will be on your table. Your textbook will have it. You can do just a quick Google search, and there's multiple different tables that are available for you to review. So let's take a look at the first problem here. You see that we have a car being towed. It's got a mass of 1,500 kilograms. Sorry, I'm thinking about another problem. It's being towed at steady speed by a rope held at 20-degree angles from the horizontal. Friction force of 320 newtons opposes the car's motion. What is the tension in the rope? You'll notice I've got this blue field that says problem solution demonstrated here in the force situations video. So let's walk through it. This one I already had prepared. Let's see if we can get some focus. So please excuse any blurriness. This thing likes to auto focus itself. And so we draw the picture of the car being towed with your arrow tension going this direction, or the force being pulled on it. I'm going to label that T. We got our knowns and unknowns stacked up here, theta, mass. We are given the kinetic friction in this case, which is 320. It doesn't say explicitly kinetic, but since it's moving and it's a complicated interaction that's leading to this, we'll just call it kinetic. And then the gravitational force, I just calculated that, m times 9.8 to give you 14,700 newtons. And then we have here the free body diagram, which I drew. You've got your weight force, you've got your normal force, you've got the tension force and the kinetic friction force, and I've drawn the friction force, and I've drawn the tension force components here, where, make that look cleaner, tension times the cosine of theta, and this will be tension of the sine times ty is going to be tension sine of theta. We can clean that up for you there. And there's your free body diagram. And we say, okay, well, what do we know? We know that it's true that the sum of forces in the x direction and the sum of forces in the y direction are both 0. Sum of forces in the x direction, then we set this as positive, this direction. Set this as positive, and so the t cosine theta goes first minus the friction force equals 0, and we rearrange that so the friction force is by itself. For the y components, we see that the ty component plus the force of the normal force is minus the sum, or the gravitational force, is what gives you 0, leads to no acceleration, and we can rearrange this. However, let's take a look at this over here. The question says, what is the tension in the rope? You'll notice that we know the coefficient, or that we know the angle, and we know the kinetic friction in whole, in total, and so we can substitute in those values by rearranging solve for T and run the numbers, and Bob's your uncle, 340.537 newtons, or a tension of 340 newtons once you round. That could be 341 newtons. I think if we can do 340 newtons, we should probably be able to get that extra 1 newton with our measuring device. So I'm going to write it as 341. The textbook will say 340. 341 newtons, and as you can see in the solution, that is in exactly 340 degrees. Let's move on to the next problem. This one, we're going to work from scratch. I did this problem in lecture, and it didn't go exactly great at first. Here we have cabinet on an incline. So we have a 50-kilogram steel file cabinet in the back of a dump truck. The truck's bed made of steel is slowly tilted, so we have steel on steel surfaces. And the question says, what is the magnitude of the static friction force when the bed is tilted 20 degrees? And then what angle will the file cabinet begin to slide? So wiping away what I worked on before and just focusing on talking about this as we are now. What do we do first? As always, we sketch. Let's not over exaggerate our sketch here. And we got our cab here. It's got our driver, whatever. And there's the cabinet right here. What are our knowns and unknowns? We have theta initial, which is going to be 20 degrees. We have a 50 kilogram cabinet, 50.0 kilograms, and we're going to probably anticipate using G, so there's 9.8 meters per second squared. And then the question is, what is theta max? What do we need eventually for theta max? What is our friction force, which I'll use lowercase script f for friction, equals, this is, let's call that initial. What do we do first? After this is free body diagram. And so we draw our box. This is going to be initial. Kind of a wonky sketch there. Theta right there, theta initial. And we draw our FG, F normal. We've got components of FG cos or sine theta here. FG cos theta, because remember this angle here corresponds to the angle here. This becomes the cosine, even though it's along what we're going to call our y direction. And sine goes along the x direction. So this is something that we've done different than we did before. So make sure that you're keen on recognizing where your angle is. There's theta, theta initial down here. Clean that up for you. Friction force opposes motion. It wants to slide down, so we're going to put the friction force F static initial right there. There's your free body diagram. Ready to go. Is it acceleration? Accelerating? Acceleration is 0. So for part A, say what is Newton's first law? Is it Newton's first law or second law? In this case, it's not moving, so it's in the x and sum of forces and the y equals 0. Let's take a look at the sum of forces in the x first. This is going to be Fg sine theta minus the friction force equals 0. When we punch this in, this becomes Fg is 50 9.8. Fg is 50 times 9.8 490 newtons. And so F of S sub 0 is Fg sine theta, or 490 times sine of 20 degrees. Sine 20, enter 167 newtons. Suppose you want to try it this way. If you start out using the definition of static friction, this would be, let's write this like this, mu sub s, and then normal force. We can't use this. We're going to get a number that's too high. And the reason that we can't use this number, and because it's too high, is because this is the maximum value. Remember that the static coefficient of friction is a range. It's less than or equal to. So we have a friction force here, 167, and when we punch this in here, where m sub s, mu sub s, for steel on steel is going to be 0.60 units, this won't work, because this is the maximum static friction. So let's take a look at B, where this comes into play. In part B, we have the same effective configuration, just a different angle theta. And here, this is theta max. This is still the force of gravity, F normal force, but because the angle is presumably larger than 20 degrees, this F normal is going to be a different value compared to the original one. Component going this way, Fg sine theta max. We don't know what that value is, so we don't want to use cos theta max. We don't want to use 20 degrees here, so we got to put a subscript there that lets us know that we're being more careful. Fs max is this way. We don't know the angle. We don't know this static coefficient of friction that's going to keep this at rest. So we're kind of stuck in doing this just yet. But let's go ahead and do sum of forces in the x just to see what happens. Sum of forces in the x direction, say Fg sine theta max, I'm just going to go m, equals, or minus, sorry, minus F sub s max equals 0, or Fg sine theta m equals Fsm. So in order to get this angle, we need to know the mass, which we do, and the static friction, which we don't know. We need more information. So let's put this off to the side, and then we're going to take a look at the sum of forces in the y direction, which are, we got the normal force going up minus Fg cosine theta max equals 0. How's this going to help us? Well, we can rewrite F, the normal force, is equal to Fg cos theta max, which I'll go ahead and drop that x and just kind of thumb at theta m, and max takes the equal sign, the maximum value, mu s f sub n. We're still in static coefficient of friction, so we don't change this from 60. We're going to keep the 60, but now we can have an expression for this. So let's plug these in. 3 into 1 Fg sine theta max equals, this is now, this that value gets mu s f normal force, then 2 into 1 again gives us Fg sine theta max equals mu sub s. Doesn't change, but the normal force is now Fg cosine theta m. And notice what happens here. Can't believe that did that. So notice what happens here. Both of these have the force. We can drop that out and solve for the angle theta. This becomes sine divided by cosine equals mu sub s, or that's tangent. Thus, the max value, this is a kind of an annoying problem. This is a problem that wouldn't show up like this on a test, but it's important for you to see all these relationships in here. Inverse tangent of mu sub s, which is less than 1, which is really what you want anyway for that. So we get tangent inverse theta, and this should be 0.80. I know I said 0.60 earlier, but I misspoke. That's 0.80. Theta max is, let's do the calculation, tangent of 0.80, 38.65 degrees, or 39 degrees. And that's how you look at this type of problem. Very unlikely that you're going to see a problem with this much theory theory driving, but it's important that you really get a chance to look at the friction force, static friction. Here it is. It's at some angle where it's not going to slide. You're at a much lower static coefficient compared to what it could be. This value is closer to 365 newtons. You're well below that because you haven't lifted that up. This is experience that you have with lifting things up at home. If you tilt the table too high, stuff starts to slide off. If you lift the plate too high, stuff starts to slide off your plate. So you know you get this part. This part gets a little hazy because it's like, okay, which coefficient do I use? We use the static coefficient because it still hasn't started slipping. It hasn't started moving across the surface. It's still at rest compared to the surface. So we keep that maximum value because, again, when you go back up, you see that static coefficient goes all the way to the top, the maximum value, before it slips into that kinetic region. So hopefully that makes good sense, and this is the answer that you get. If you have any questions, let's chat. Let's do another problem. Sometimes you can have two boxes that are in, or two objects that are in contact with each other, and you want to be able to do the calculation of the forces between those two, or if there's friction on the surface, that sort of thing. Let's take a look at this one. Here we have two boxes, a 5 kilogram block and a 10 kilogram block, and the 5 kilogram block is being pushed by 3.0 Newton force. The two blocks move together. What force does block A exert on block B? Okay, so let's go ahead and sketch this out. And let's make it kind of big this time just to really be able to see all the things that are happening. This is block A and this is block B. We apply a force here onto A, which means, and we'll sketch that in a minute, that force is applying onto applied force. I'll just leave it as F later on. This is a frictionless surface. So we're going to not worry about friction, but friction can be involved and could be involved on a test question. No guarantees. Mass 1, 5.0 kilograms. Mass 2 is 10.0 kilograms. I'm so tired of that. Not down enough decimal places. The force applied is 3.0 newtons. And the question says, what is the force that block A exerts on block B? So which we'll call that FAB. Well, what do? As always, free body diagrams. Let's do one for each block. Block A, you have FA in the gravitational force, or I might just, for simplicity going forward, I'll just drop that and go directly to MAG because we're given masses very commonly. So remember, we're drawing these from the center of the mass, and so that's MAG. This is going to be a FA normal. And then we have a force that's acting this direction. Let's move A up to here, like so. And this is going to be FA acting on B. I'm sorry, my mistake, I apologize. This is the force acting on A, so it's going to be the applied force, or just F with no subscript in this case. Are there any other forces acting on this block? While you think about that, I'm going to start setting up stuff for B. There's block B, again, MBG, FB normal force. There's a force acting on this one. This one is FAB. Are there any forces acting this way on block B? Let's go back to block A for a second. Is there any forces acting on block B? If you say you're not sure, ask yourself this question. Is there anything that's pushing back on block A? Remember, force is not always something that's motivating a change in motion, but is resisting a change in motion. Because block B is in place here, this has inertia. It doesn't want to move, so it's going to push back on block A. And so even though we have a force FAB acting on block B, there's an equal but opposite Newton's third law force acting on this one, so that's one's going to be force B on A. Notice I changed the order of the coefficients here in order to take advantage of that understanding. That's Newton's third law thing. As for block B, there's nothing on this side to the front of it that's acting against it, that it's got to resist against, and there's no friction acting to also to oppose motion, which we'll say is going this direction. So now let's write, we've drawn our forces, and the next question is, okay, let's do our sum of forces. Since there's no friction, here's a quick tip. Since there's no friction, we very rarely need our y component of this mass. So we're going to stick to the horizontal in this case. Let's do that with sum of forces in the x for A are 0. That's going to be big F minus FBA equals 0. F equals FB on A. That tells us that this is, in this case, we know that this is 3 newtons. That means that this is 3 newtons. Does that make sense? We'll swing back to that in a moment. All right, let's put a button on that one. Let's come over here and look at sum of forces on B in the x direction. As always, we have to ask ourselves, Newton's first law, Newton's second law, what's happening here? This would give you the immediate impression that this is sum of forces equals 0, especially if you inadvertently drew your arrows of equivalent mass length. But the question you have to ask yourself is, okay, is the system accelerating? Do you have any reason to think that this system is not accelerating? This one can lead you to think that there may or may not be acceleration. This one, it's almost inescapable. There must be acceleration because there's an unbalanced force here, a single unbalanced force. This is undergoing Newton's second law. So we're going to put A there, MBA. Over on this side, then that means that this also is moving at acceleration. That's going to be mass of A accelerating at A. Are these the same acceleration? Again, unless we're told something like A merges into B or there's some kind of change in configuration, we cannot make an assumption about this. And so there's no reason to think that these blocks change in any way. And so the acceleration of the two blocks is going to be the same. Okay, so sum of forces in this direction, force minus, again, this is going to be positive acceleration. And so force minus FB on A is equal to MA or M big A, the mass A block moving at acceleration. Over here on the right one, we have MBA. And the question says, what is the force that's being exerted between these two? Well, since Newton number 3 says, since we know that Newton's third law says equal and opposite reactions, remember the signs are already being taken care of by our configuration. So we don't need to apply signs, but the magnitude of, why does this thing keep going like that? Since Newton's third law, since this is already taken care of the signs, we only look at the magnitude of your forces. FB is equal to the magnitude of FAB, and so we can just use FAB, substitute in here like so. Sub FAB into equation 1, which it is, equation 2. And so we write it as such. Now, let's solve this for A. Because A is the unknown that we have. So we have A is unknown in both equations. FAB is the same in both, and we know the value of the force. This is a value that's known. Not sure, we can know the mass. We can solve for A and substitute that in here and get rid of it. Solve for A in 2. So this becomes A equals FAB divided by mass B. Sub into here, so we have F minus, this stays, FAB equals mass A times FAB over mass B, or the ratio MA to MB times FAB. A little bit of algebra. This becomes, add this to both sides, that becomes 1 plus that, 1 plus MA over MB, FAB equals force, or equals F times, this is MB plus, this is MB over MB, so MB on top over the sum MA plus MB. Let's throw numbers in there and see what happens. 3.0 newtons times mass B, which is 10 kilograms, divided by 5.0 kilograms plus 10 kilograms. And if you're looking at the numbers, you can kind of see this becomes 15, this becomes 30 up here. So let's just do the numbers. 3.0 times 10 kilograms divided by, open a parentheses here, don't trust the order of operations, it'll lead you astray. And we get 2.0 newtons. And that is the correct answer. Let's ask ourselves a question. Does this make sense? That's the big question here. Does this make sense? The reason it makes sense or doesn't make sense is because whether or not it fits what we've been working with so far. Let's take a look up here. Let's take a look up here and see. All right, so this is 3 newtons pushing on A. Is the full 3 newtons going to move B? It can't. Some of that force has to move and accelerate A. So it should be a smaller value than the force that's applied to A. Second, it's reduced, but it's still larger than what appears to be the net force acting on A, because if that's 2 newtons, then there's 1 newton that's acting on A. 2 newtons for the B. B has a larger mass. It makes sense that you need more force acting on the larger mass in order to keep it accelerating with the system in the same way. The ratio is 2 in this case, to twice the mass, so twice the acceleration. Twice the mass, so twice the force to accelerate these two at the same rate. Good job. Let's take a look at another one. The next 2 problems that we look at are going to be pulley problems, ropes and pulleys. And we're going to be looking at a plethora of details here. So make sure that you're thinking about everything as we go along. This is going to be example 5. Bank robbers have pushed a 1,000-kilogram safe up to a second-story floor to ceiling window, meaning no ledge, no window frame ledge. They plan to break the window, then lower the safe 3 meters to their truck. Not being too clever, they stack up 500 kilograms of furniture, tie a rope between the safe and the furniture, and place the rope over a pulley, and they push the safe out the window. What is the safe's speed when it hits the truck? The coefficient of kinetic friction between the furniture and the floor is 0.5. So we got a lot to unpack here. Let's start doing that. All right, so here's our safe, or here's the, I'll draw it as a chair. There's our chair, and they've got this tied by a rope over a pulley to the safe here. The safe's going to go down some distance of y initial of 3 meters to the back of the truck. Y final equals 0. And we got some masses of things and a coefficient of friction, so let's write those things down. We got a safe that's M safe is going to be, I don't want to use an S, we're just going to leave M2. We'll call this M1, M2. Mass 1, we'll get to that in a second. Mass 2 is the safe is 1,000 kilograms. Make sure that you've worked out before you do this exercise, right? 500 kilograms. That is going to be the chair, the furniture. Okay. We've got a coefficient of friction, mu. It says kinetic, so it's going to be mu sub k. Remember, mu sub k is a constant value for two surfaces sliding. Presumably, it'll change at like extreme situations, but we're not dealing with extremes. We're going to lower that distance 3 meters. Y final equals 0. I'm sorry, yeah, Y final, Y initial is 3.0 meters. Okay, looks like we've got everything. Oh, this is 0.50. Notice this is unitless. There's no value there. No units there. Mu sub k is a scaling factor. The more they stick together, the more force you need in order to overcome friction. Okay, so we got all our pieces here. What do we do? We've got two masses. Let's do their free body diagram. Mass 1. We've got mass here. You know that there is M1G. You know that there's the normal force 1. We know that there's a rope going this way. We're going to call that tension. And friction in this case is told. There's friction here. So we're going to do F sub k over here. Acceleration is going to go to the right. And in this case, it says how fast is it going when it hits the truck. So we're going to presume acceleration. And we're going to call this sum of forces in the x is accelerating. For mass 2, we have the safe. You have mg. Well, you have to be careful here. You don't want to add too many forces that don't exist. What force is this? Take a moment and think about that. Pause this video and think about it. What is the force here? Here it is going over the pulley. This is going to be your tension force. Do we need a normal force? And the answer is no. No normal force here. This is not on a surface. This is hanging from this is hanging from a tense rope. That's not stretching. It's not doing anything else, but it is a taut rope. there's no need for a normal force. So make sure that for a hanging mass, you don't put any normal force. There is, however, the acceleration of the system. These are presumed to accelerate the same way, just like when you saw the two masses butted up against each other. And so again, sum of forces here, and the y, we'll call this 1x and 2y equals m2a. These accelerations, once again, are the same acceleration. We have friction here, so we're also going to need sum of forces in the y direction, but in this case, no acceleration that way. That one is 0. We are now ready to start solving this problem. Okay, so let's see here. We're given everything, so we need to be able to get a tension here. So we're going to have to solve this problem, this part of the problem first to get that tension, and then put it over here, stuff it in, and solve for the acceleration here. Here's the catch. We've also got this acceleration here. It's the same acceleration. So we need to blend these two together and get rid of tension altogether while solving for acceleration. So let's get started. First, sum of forces in the x direction. T minus friction, kinetic friction equals ma. As soon as you see this, you should be thinking about that kinetic friction definition. T minus mu k normal force equals m1a, where kinetic friction is that. So this is just about ready to go. We can go ahead and leave t here for the moment, and we'll see if we need to arrange that. So we'll pause that there. We need to know t. This is something we need, that normal force. We've got the we don't know the tension. We don't know the normal force. We don't know the acceleration. We know the mass. We know the coefficient of friction. We need something else. We can get the normal force looking at our sum of forces in the y direction. So then sum of forces in the y direction for the first object is 0. That's going to be F normal force 1 equals m1g. I don't want to skip steps, so that's going to be that F num1 equals m1g. Straightforward stuff. Okay, so then thus T minus mu k m1g equals m1a. Now we're down to two unknowns. This is good to go. Next, let's start solving this problem. This is going to be acceleration is going this way. So this is the dominating force. This is going to be m2g minus t equals m2a. We can solve this one in here. You can see that this is t minus rewrite, so we don't think that it's just a fraction. Rewrite this as t equals m1 of mu k. No, we don't want to combine those. Mu k m1g plus m1a. This is what's going to come into this equation. m2g minus t, which is mu k m1g plus m1a equals m2a. You got to keep track of your coefficients. This is just an arduous problem in this way. And then m2g minus mu k m1g equals, this is a minus sign, becomes plus m1 plus m2 times a. There's some algebra here. If you don't see that right away, show the intermediate steps yourself. See how you get there from this. Okay? That's a k out of 12. This is mass 2. We can plug in numbers now if we want to get acceleration. Why do we want acceleration instead of tension? The question is asking for a final speed what's its speed when it hits a truck. So V final is going to be 0. V naught is going to be, it's going to be unknown. This one's meters per second. We're looking at kinematic equation here. I'm sorry I didn't get to that right away, but hopefully this is becoming clear to you as we're going this way. So M2G, M2 is 1000 times 9.8 minus 0.50, mass 1, 500 times 9.8 equals 1000 plus 500 times acceleration. Acceleration, we end up with 1500 A equals, we're going to just swap the sides here, 1000 times 9.8, close parentheses, minus 0.50 times 500 times 9.8, and we get 7350. Divide both sides by 1500. A equals 4.9 meters per second squared. Notice we set this acceleration to be positive. In the textbook it says it's negative 4.9, but we're going in the direction of the acceleration, not absolute positive up. And so that's why this is positive acceleration as opposed to negative. Then kinematics would be, we need a final velocity. We have a final velocity, initial velocity, and different heights and acceleration. This is going to be V final squared equals V naught squared plus 2A delta Y. V final is what we're looking for. V naught plus 2 times, you have to be careful here because this actually is going to be wrong if I do this, if I don't do this right. This is going to come out negative. This is the safe way to do it because our kinematics are set to be absolute positive. And so this will be negative 4.9 meters per second squared times Y final minus Y initial is going to be 0 minus 3.0. That gives us a negative. So we need to make sure that comes out positive. V final squared equals 2 times negative 4.9 times negative 3. We get 29.4. Or V final is 5.42 meters per second. And that's what we get. We had a system of equations moving here, and we ended up landing looking at a kinematics problem. But now we have the tools to work with an expanded universe of tensions and forces that are causing accelerations, and the accelerations can then translate to kinematics. It is going to fill a page sometimes. Finally, we're going to look at a similar problem, only in this case we're looking at one of the masses is on an incline, and we've got an acceleration, we've got a tension, we've got a coefficient of friction to determine. So we've got a lot to do on this problem. We may even go into a second page on this one. So let's get started by taking a look at this one. This is going to be number 6. And we've got this guy here, like so. This is the angle theta given to us. We got mass 2 going over this. We got mass 1. And based off of the sketch, it looks like our motion is indicated this way over the top of the pulley. From the data of the thing, we see that mass 1, that's the one that's hanging mass, 4.0 kilograms, mass 2, 9.0 kilograms. Connected by a light string. Light string means massless string. We're going to ignore the mass of the rope, the string, whatever that's connecting the two. Passing over frictionless pulley, as shown. The object mass 1 is held at rest, so we have an initial velocity of 1 is 0 meters per second. And there's going to be a final, maybe. Oh, looks like the motion is going the other direction. But this says that it's at rest on the floor. M2 rests on an inclined plane at an angle of theta, 40 degrees. Release from rest, M2 slides 1 meter down, delta x ramp equals 1.00 meters. And this is going to go up 1 meter in 4 seconds. Delta t is 4.0 seconds. 4.00 seconds. I'm really not going to pay too much attention to the sig figs. It's good to know about them, but it really slows down because of the consistency issue. Okay, free body diagrams. So free body diagram, mass 1 is your block. We've got M1G, tension in there, no normal force, no left, right, and acceleration is going to go positive up that way. This is sine theta. This is M2G cos theta. Normal force. I'm not going to put a subscript beyond normal because it's the only one that's hanging on a surface, so I don't want there to be any confusion. Friction in this case. Which direction is friction going? Well, we expect motion to go this direction. No friction over here. Acceleration. We have friction going this direction. What kind? Kinetic. This is a null point. Sum of forces for 1 in the y direction is going to be m1 acceleration. Sum of forces in the, and we're going to draw this right here, x and y on the ramp is going to be m2 accelerating. And sum of forces on the y direction up here is going to be m2, is going to be 0. It is m2a, where a is 0 along that direction, and we're going to keep these 3. So let's kickstart things. Okay, mass 1. We've got sum of forces in the y, m1a. And so that's going to be tensions going in the direction of that, T minus M1G. This only works if you write this in the way that the acceleration of the system is consistent between these two, and you get that. I've got this arrow down here, but I guess we're just not going to worry about that. But if you did work it this way, you should get the same results if you had it assuming the other direction. It'd be weird, but with the kinematic factor on this problem, it complicates our thinking, so let's keep it simple. We got the acceleration going this way, tension minus M1G gives us M1A. The question doesn't say anything about the tension, but it does ask for the acceleration, so let's go ahead and just write this as M1G plus M1A. This is our first equation. Mass 2, let's jump right into it. Sum of forces in the x direction, M2A. This is going this direction, so M2G sine theta minus F sub k equals M2A. Oh, and I forgot something here. So there is a tension force here. Thanks for catching that. I know you've been waiting on me to get it fixed, but there it is now. It's in place. So we've got a tension force plus this. Minus the coefficient of friction. Minus the friction force, rather. So this is 2. So we'll go off to the side here and do part A. We get going, we see the tensions, we want to work through it. We need to know that coefficient of friction, but we can't do that until we have the acceleration and thus the tension of the string. So we've got these accelerations here. Is that going to get us where we want to go? The answer is no. We're going to use kinematics. We have initial velocity, we have a displacement, we have a time. Okay, so even though we're letting mass 1 held at rest, we're letting the system at rest be released from rest, so they both have that same initial velocity, 0. So we have initial velocity, we have a time, we have a initial velocity, we have a time, we have a displacement. This looks like our kinematic equation that looks like this. Delta x will say along the surface. We could do delta y and looking at mass 1, but remember those equations don't use the mass at all, so we don't need to know the mass. V naught xt plus 1/2 at squared, where we don't know the acceleration, but we know the displacement, we know the velocity, we know the time. We have everything we need. 1.0 meters is equal to 0 because that started at rest, plus 1/2 a t is going to be, what is that, 4 seconds squared. 1/2, 4 squared 16, half of that is 8. 8.0 times a. Acceleration is going to be 1 divided by 8. 0.125 meters per second squared. Says what's the tension of the string. We now know acceleration. We can use either one of these two expressions. This has the coefficient of friction in this, so we can use for part B, we can use this guy. Part B equation, use 1. T equals m1g plus m1a. This is going to be 9.8 plus 0.125 times the mass. Mass 1 is 4 kilograms. Tension in the pulley is 9.8 plus 0.125 times 4, 39.7 newtons. Notice that this is an increased value from either one of those two. The hanging mass is pulling down. The mass on the mass is being slowed down because, or is being accelerated upward because of the mass that's pulling along the surface of the ramp. So this should be a number that results from adding two values together. One into 2, and we're going to see this becomes m1g plus m1a plus m2g sine theta minus f sub k equals m2a. We know the masses, we don't know the acceleration, and in order to get the acceleration we also need to know this. So let's go ahead and find this real quick. Our last sum of forces is sum of forces in the y direction for mass 2 is 0. Normal force minus m2g cos theta equals 0, or as you can see where it's headed, that normal force is equal to m2g cos theta. Then we know that the kinetic friction is mu k normal force, or mu k m2g cos theta. A lot of terms here. Don't forget your terms. Don't miss anything when you're rewriting. I'm going to move everything over to the one side and all the accelerations onto this side. So this will be m1 minus m2. So I'll write algebra. And that's going to be times acceleration equals m1g, m2g, all this stuff right here. So this is negative, it's going to become positive, so this is going to be mu sub k. I'm sorry to condense the multiple steps in here, but I want to make sure that we don't overdo it here, and that the time, keeping time in consideration as well. This minus m1g minus m2g sine theta. There's our cosine, there's our sine, they're both here. There's our equal sign, so our equation is done. 1, 2, 3, 4, 5 terms. 1, 2, 3, 4, 5 terms. So, what a big process. Let's go ahead and just throw numbers in, and that'll let us simplify this down. This is m1 minus m2, or 4.0 minus 9.0 a. We know the acceleration is 0.125 equals mu k. This is mass 2, 9 times 9.8 times cosine of 40 minus, may have a bunch of minus signs that cancel each other out, m1g 4 times 9.8. Sorry about the mess here. Limited space. Trying to keep it all on the same page for the moment for me, so I can show you that way. Sine, minus m2, 9 times 9.8 for that, sine of 40. And I'm going to go through here and clean this up one term at a time and then simplify. So this is going to be 4 minus 9 times 9.8, I'm sorry, 0.125 negative 0.625 equals mu sub k. Let's put a coefficient on that. 9 times 9.8 times cosine of 40. That's going to be 67.56 mu sub k minus, let's hope this works out. This is a lot of big numbers. Times 39.2, that's this term here, and then minus 9 times 9.8 times sine of 40 degrees. That gives me 56.694. Algebra 67.56 mu sub k equals, these added to each other onto the other side. So 39.2 plus 56.694 minus 0.625 gives 95.269. Mu sub k is 95.269 divided by 67.56. This may not be great. It seems like it's bigger than 1. All right, 0.125 is confirmed. 39.7 is confirmed. I got some bad algebra going on. Oh, I did, wait, nope, I did mess up. Okay. So I get this wrong number here, and I have to go back and check. Why? How do I know this is the wrong number? This is greater than 1. That's not going to work. So where's my error? Well, this is still a reasonable number. This is still a reasonable number. And it turns out these are actually the correct numbers. But let's go back and look. I threw this tension on here because I had overlooked it. And I threw it on here incorrectly, adding tension in this. You probably caught that as well and been wondering, what the heck is Dr. Tracy doing? Well, the correct answer is doing the math wrong. So this should be subtracted. Here's what I'm going to do about this. M2g sine theta minus t minus fa. All right, so that means over here, when I make the substitution, I make the tension substitution. Tension goes in here. This becomes m1g plus m1a. That's a minus sign goes in front of this. Minus sign goes in front of this. This remains unchanged. This remains unchanged. That remains unchanged. So let's see the impact. I moved M2A over here. So it'd be negative M21A plus negative M1A, negative minus M2A. So there should be a negative sign in here. So I'm going to put a negative sign right here and make that positive. This adds those together. Again, check the algebra. You'll see that I'm ending up in the same space. So this becomes a negative sign and a plus sign right here. Over here, everything else remains, well, there's that M1G. That's negative. That comes over here and becomes positive. That becomes positive and positive. Let's see if this fixes my numbers. And if I get this wrong, I'll just rewrite this on a new page and rework it, showing the correct math. But I believe I've caught all the errors. So now we got 39.2. Whoops, sorry. So we have negative 1.625 minus 39.2 plus 56.694, and we get 15.869. Now we solve this and we get 15.869 divided by a bigger number. That's promising. This is going to give us something less than 1. Divided by 67.569, and we get 0.235. That's less than 1. That number makes sense. And it is, in fact, the correct answer for part C. Okay, I hope this helps. If you have any questions, just let me know. All right.